Professor Roberto is a professor here at the Instituto de Física Teórica, Unesp, and he's also one of the professors that is responsible for me to be here managing this course for you. Roberto used to organize, I hope he organizes again, summer school in biomathematics. And I was one of the students. I think some of you were also here in his course. So he used to organize this course during January, I guess. Only January, right? And sometimes in July. And Bahia, you did in July, right?
In August, actually.
August, yeah. So this course was, most of the time, was more related with ecology and epidemiology, and I think maybe the whole idea of the program that you have right now was a lot inspired in the course that Roberto used to organize, and it's because I was one of his students, and also because I was one of the tutors during the program since 2011. I guess, a long time ago.
Ages.
And I hope you enjoy a lot. I enjoyed a lot when I was a student, and I still enjoy a lot. I learned a lot with Roberto how to teach students, how to teach in the interdisciplinary part of the knowledge, which is a big challenge. And I hope you enjoy a lot. And let's pass to the formal part. Roberto is a physicist by training. He did his bachelor here in the Universidade de São Paulo. And then he did his PhD also here in USP, and then a postdoc in France. Currently, he's here as a professor at the Institute. And he started in a very different field. He started in fluid mechanics, hydrodynamics, and waves. So for those that are physicists, you see that you can be in a very different background, very different program, and then turn biomathematician. And we are very, very, very lucky that Roberto decided to shift his career to biology, ecology, and epidemiology, and be this person that is helping us to join different fields. He's also one of the heads of the Observatório COVID-19 BR, which is a group of researchers that decided to understand what was happening in Brazil with the data that we had access in Brazil, and understand how the dynamics here of the disease were happening. And I'm very lucky I was part of this team as well. I learned a lot during this time. And nowadays, Roberto is a researcher mainly in epidemiology and population ecology somehow. If we say that epidemiology is part of population ecology, he is also an ecologist. So I hope you enjoy a lot. Make many questions. Roberto loves to answer questions. We need to find a box for him because he leaves a box on the back of the room for the questions, right, Robert?
Oh, yeah.
We need to find a box. And that's it. So help me to welcome Professor Roberto Kraenkel.
Okay, so thank you for the kind words. A little bit exaggerated about me. And is it okay? Okay. So good morning, and so this is the first course of the program, and it's meant to be a very basic introduction to population ecology. Right? So. Before I start, I want to have an idea of your backgrounds. Okay, so who has the main background in physics, mathematics, computer science? Raise the hand. Okay, so you have some of you, yeah. and who has a background in biology and related things. So that there's a majority of biology background. Is there anybody that was not in the two cases? Okay. You. What's your background?
I'm from management and management control. I'm from management and management.
Management. Okay. Okay, so I need to erase this. Let me give you first an outline of the whole course, what will be the subject, okay? So today, obviously, it's an introduction, okay? So introduction, I mean, the subject will be always population biology applied to ecology, and at the end, a little bit of epidemiology also, right? So that's the subject, it's the main subject. So we'll have an introduction and basics today. Well, I won't say class by all the classes, but just the subject. Okay, so today's the basics, and after the very basics, which is exponential and logistic growth, then we will have again basics, but in some other setting, which is when we count the time, not as a continuous time, but looking at the time as 1, 2, 3. So discrete time. This is called discrete time. So then we come back to the first first part with continuous time, and we will study species interactions. Right? So at the beginning, we will study just one single population of a single species. And then we want to study how species interact, which will be essentially 3 types of interactions. One is predation or antagonistic interaction, competition between species, and mutualism between species. Mutualism is usually just a half an hour because it's either very difficult or either very elementary. And then we will move to what's called a community moduli, which is for us 3 species. 3 species interaction. So you have predation mixed with competition and so on, this kind of thing. Okay, so the next we will move to some 2 or 3 classes of epidemiology, which is in the setting of population dynamics. After that, we will have some application of everything that has been discussed, which is will be used an example on the subject of desertification, which will allow me to introduce concepts which are called alternative stable states in ecological systems. Alternative stable states in the jargon of physics is just bistable systems. Right? In the jargon of ecology is alternative stable states. And in the jargon of physics also that's related to something called hysteresis. And so, and if you have time at the end, I will have at least one class about metapopulations. So I won't go into the detail of what metapopulations is now because we have not even started. So this is more or less the general outline. I will adapt the pace of the course depending on you a little bit. Okay. So I really like if you pose questions, interrupt me, and let me be a little bit more precise also. One thing is we have a mixed population, a mixed class with people that have very different backgrounds. Okay? This means that sometimes people don't understand the word because it's jargon of one area or of the others. Okay? So for biologists, evolution is something that's it's usually something, a word that's connected with evolution of species and so on. But in physics, evolution is time evolution. And people get what? Where's the biologist will say, but it's not evolutionary. And the physicists will say, this is not time. So many times you have this. And then you have to also to stop me, say, I don't know what this means. Okay? No problem. Yeah. I know that. Yeah, just. So that's it. Please pose your questions. If you don't pose, I will pose to you. Okay? Well. Okay. So let me start with some general observations, let's say, it's like prolegomena. And so what is the basic question? Just one thing. I teach on the Blackboard, okay? I don't have PDFs to distribute and so on. Okay? And at the end of the class, I will make some recommendation of books. Every class, I bring some books for you to take a look and see how they are and so on. So there will be a recommendation of books where you can study this either more mathematically or more on the biological. I bring books from both sides. So the basic question is, okay, first, before the basic. What is a population? So, okay. So, if I want to start the course with what is a population, we get lost because it's difficult to define. Usually, we will be thinking of a group of individuals, okay? And normally, a population will be associated to a species, okay? But not necessarily. For instance, if you want to study, say, vegetation dynamics, you want to not necessarily know all the species. You want to, say, measure coverage of an area by, say, an extent or biomass. So biomass can also characterize a population of, in this case, of vegetation, of plants. Okay, and so it's not connected to a species in this case. Okay, so that's why this is sometimes, from fundamental point of view, difficult to have a precise definition, and also for microorganisms, there are situations where it's difficult to define a species. And also, for instance, if you look for dynamics of plankton in the sea, you don't want to necessarily, you want to know the mass that you have of plankton there, not all the mass of species 1, 2, 3, 4, 5, 6. Okay? So that's it. So population will not be defined in a formal way, but I think everybody understands what we mean by population. So the main question that starts our course is, why do the size of populations change in time or if constant, what determines the population level? we will look at populations, and they may change in time, okay? So you see immediately, if you come from a biological background, that things that are measured, like number of individuals of the population, and they change in time, you need to describe this mathematically, okay? And you need to know how to describe changes in time. Right? That is what introduces you, brings the need to know derivatives, differential equations. Okay, so, okay. So, but not all populations change in time. Now, some of them that have constant levels, and then you want to know, okay, why are they constant, and what's the mechanism that makes that they don't change, okay? So this is the main framework, the main question, and this is connected to, in the jargon of ecology and population dynamics, the first thing is why population change in time. This is connected to what we call the population dynamics. And the second, what determines the levels, if they are constant, it's called problem of population regulation. Okay. So we will be concerned with both. So the framework is how will I mathematically describe a species, okay? But this probably is, most of you think it's obvious, but you could also think, how would you describe the population of students here? You could name everybody. What is the framework when you say of populations, population dynamics? So we will describe the population by its size, number of individuals, or if it's biomass, then it's by biomass some unit. Okay, so it's number of individuals. So this is the description of population. Now, when you describe a population only by the number of individuals, we have a population that we say that does not have a structure. Now, it is very interesting, and this will happen a lot. You will have also group work, and this will you will see this. There are also some populations that you say that are population with structures. Okay? Structured population is for instance, the fact that you have population, you have males and females, and you can say the number of males and number of females, or you have individuals that are tall and others that are not, or any relevant property that maybe has an influence on the outcome of your study. Then you can subdivide your population on other populations and put a kind of label on it. Okay, the classical thing is male-female distinctions, for instance. Okay, but not only. For instance, it's very important in certain situations. For instance, the dynamics of, certain fishes. Fishes have ontogenetic shifts, means that they start in very small size and then get very large. So you have to the population, and then they will interact with the fish, or will be interacting with other species. The size is obviously very important, and the kind of interaction that an individual can have. If it's a big fish, it's different from the small fish. So you have to put a structure of size in this case. Okay? Also, what's very important is to divide sometimes the population in juveniles and adults. And juveniles are by definition they do not procreate, they do not give birth, and then the adults do, and then different time spans, and from the adults, from the juveniles, or even from older age. So sometimes you have the structure of ages, right? Which can be from just juveniles and adults, but to a almost continuous age of the individuals. Okay, this is, for instance, very, very important in epidemiology. Well, I've worked a lot with models for COVID-19 in the last two or 3 years, 2 years, and 3 years. And one of the things that everybody now knows from the news is that the mortality depends on your age class. Okay, so if you want to describe about human population and how an epidemic goes through this human population, and you want to infer what would be the number of people that can die if something happens, then you will have to have a population which is subdivided in age classes. So this is also a structure, and any model that wants to be realistic in epidemiology has to have age classes. Otherwise, it's just fantasy. Okay? So we will start, therefore, by describing populations without structure, but structures will come in very naturally in your exercises and so on. So, and I will use a continuous function of time. This is the number of individuals in your population. Okay? So, to describe ecological dynamics, what do you want? So we want somehow to describe the change of the size of the population and we want to write an equation. Okay. So this will be described by a mathematical function. Okay, it's the number of individuals. Okay, n of t. Right? It's the number of individuals. Now, we want to know what we want to introduce biological mechanisms at the level of the population, okay, that produce change. Okay, what can make a population size change? Tell me, you. Birth and death. More? Migration. Environment. And yeah, essentially it's always birth and death, okay? But I mean, then you can have different kinds of birth and death. I mean, death can be through just aging, or senescence, or the guy gets eaten, or many mechanisms that induce death and also birth. Okay, if you have, so you want to somehow write an equation: change of the population equal to biological mechanisms. No, that's what we want. Write an equation where we have the change of the population on one side, and the other side we will have to translate mathematically the biological mechanism. So in this point, that we will say we are making a model of how the mechanism is acts. Okay, so birth, death, and all the predation, competition, all of this has to be translated into mathematical functions. And then we have to write equations, which on one side you have the change of the size of the population, on the other side you have your biological mechanisms. Okay? Now, here, this is the difficult part. Okay? That's why population, but it's also the interesting part. Now, we have to have an approach which we have to first do something simple, which gets the general dynamics of the population. So you say, what are the main mechanisms? Not all. So I hope that I've experienced with people from an ecology and epidemiology, whatever, and that people try to describe usually too many mechanisms, which creates super difficult theories here. It creates models that are impossible to. So there is a kind of art, a kind of what do I put into the model on what I don't. And this will depend on what is the question that you want to answer with your model. Okay? Even it's a very general question. Okay. Yeah. Where is the? Okay. So you know this is a complicated thing. Yeah, it's working.
I was wondering, with COVID-19, we had some physical barriers, geological barriers forming. At the same time that there was migration, there was also some speciation, I guess, processes with new variants coming up. And then I was wondering if that speciation process would be included in a
population.
Formula. Yeah.
Yeah, speciation problem. Yeah, you know, Flavia is a specialist in speciation. Actually, you can ask her better than to me. And should I turn off? Yeah, power. Yeah, there are theories about speciation. They are more computational usually. Okay, instead of having this kind of thing, I mean, you have the same kind of thing. But instead of having an equation, you write an algorithm and you put it on a computer, and then you run in the computer this thing. Okay, so it's not at the level of it's not using differential. Although you can also, I mean, you can also do speciation with. That's not part of our course because we won't discuss evolutionary dynamics. Okay. Now, evolutionary dynamics is a very interesting subject, and maybe in February you have something with evolutionary dynamics. I can't remember well. But anyhow, there is a whole. I mean, you need to know the basics of population biology in order to study evolutionary dynamics. Okay, it's also with differential equation and so on. It depends on many things you can study. You can use game theory, or you can be individual-based models, many things. Okay, now we need to describe mathematically not the number of individuals, but the change in the number of individuals. And the change in time of the number of individuals is the time derivative of the function n. Okay? So let me just check. Everybody knows what's a derivative, or are there people that never saw it? No? Okay. Now, who has already studied at least one simple differential equation? And okay, yeah, it was not, maybe. Okay, true. Okay, so yeah, okay, we are good. So what I want to write now is write this equal to bio. Okay. So I will have to describe somehow the mechanisms that make the function n change in time. Okay. So this will lead us to our first differential equation, and I will write the following. I want to introduce only birth and death, no migration. Okay? So birth has to be connected to a mathematical expression here that is positive in order to make the number of individuals increase. So dn dt, if positive, the population is increasing, and birth will lead to the increase of the population. Okay? Good. And death, mortality, will have to have a negative term, which is induces the population to decrease. Okay? So birth, I will use the following thing. That's very simple. That is the number of dn dt is the change in time of the number of individuals. Okay? So it's the individuals now minus the individuals some small time ago divided by the time interval. Okay? So this is a rate of change. Okay? It's a rate of change. Okay? Its units is population per time. Okay? We'll use this, not this phrase, but units are very important. And we will have always to think about an equation, differential equation. If it has units here of population per time, everything that appears here also has to be population per time. Okay? So I will say that the rate of change of the size of the population per capita, so I divide this by the total population. So it's the rate of change divided by the total population, is a constant, which I will call B. Positive, B and D are positive. So B is birth and D is death. So this is very simple. I'm saying that birth and death occur at a constant per capita rate. Okay? So this means that I have the population and I have, say, the birth of, say, 10 individuals per day, or the number of individuals that dies per day is also constant. So it's a constant. Okay? Obviously, this is not at all very realistic, but it will allow us to introduce the main concepts of this class, which is the exponential growth. Okay? So now, this is a constant, and this is also a constant. I can just rename this here by a new, which is the difference between birth and death rates. I will just say R, which is the reproduction rate. Okay? And R can be positive and negative. Okay? If death dominates, then it's negative. If births dominate, then it's positive. Okay? So, but it's a constant. Okay? So therefore, I can write, I can multiply everything by n and get this equation. Now, for those that have not studied differential equations or are not very comfortable or get confused, so the first thing, this is an equation, and the unknown is a function. So it's not like an equation like a second-degree polynomial where the solution is a number. Okay? The solution of a differential equation is a function of time, because we have a differential equation in time. Okay? So this is the simplest model of population dynamics, which is called the Malthusian model. People call it more or less Malthus law. Okay, so it's curious because this is more or less the founding father of population dynamics. He was not concerned with ecology actually, but concerned more with demographics and the demographical dynamics. Population were humans for him. Okay? And it's curious because there's a joke like, you know, if you are a biologist, say you could choose somebody to have a photo with this person. So let's say Darwin, for instance, would be nice, yes? And the physicists would have, every physicist would be nice if you could resuscitate Einstein just to take a photo with him. Okay? So population biologists are are not that happy, because this guy, actually, if you look at the biography, you don't want to have a photo with him. Because although they have written the law of Malthus, this was then widely used in formulating theories about eugenics and things that manage characteristics of the populations not in a very nice way. Okay? So Malthus, and this is middle of 19th century. Okay? Well, now I said the solution of a differential equation is a function, and the solution of this equation is very simple. So the solution of this equation is this, and I will in a minute say what are they. So first, this is a function of time. Here's the time. R is the parameter that I had here. So R is a parameter, and N is a variable. So okay, that's jargon for mathematics if you don't have a mathematical training. So variables is N, and the constants that appear here are the parameters. Okay, so we will have, in this case, we have a parameter that accounts for the balance between birth and death. Okay, that's the parameter. Now, and what is N0 or N0? N0 is the population at time 0. Okay, so in order to know the population, I say I want to describe the increase of population. Then I say I want to know the size of the population in 2 days. Okay, you have to say how many individuals you have at the beginning. Otherwise, it's completely no sense. Okay? So that's the population times 0. And actually, if you put a 0 here and t equal to 0, then this gets 1. This is an exponential, okay? Exponential function. This gets equal to 1, and then n times 0 is n0. Okay? So that's the Malthusian law. Wow. So this is the first differential equation of the curve, and you can solve it. Okay? Why can you solve it? In practice, although maybe mathematicians look like this for me, but in practice it's because it is something which you call linear. What is linear, okay, in the jargon of mathematics? It's practical. Here you have only the time derivative, okay? It's not the square of the time derivative. It's not the square root of it. And here you have also a term which is n not squared or to some exponent or the logarithm of n and so on. You can have many things, okay? You have only one guy here. So n to the first, to the power 1. Now this is linear. And linear equations are usually solvable. But the fact is that most of the equations, except for today, will be nonlinear. Okay? And most of them cannot be solved, but what people call analytically. So let's have a conversation about this thing. And I think this is also important for physicists to realize. So here I write the solution, okay? But many times I cannot write it. Why? Well, if you ask a typical physicist, I say, what is analytically solving an equation? Analytically. It's writing the solution in terms of known functions. And known functions are polynomials, are exponentials, are logarithms, are trigonometric functions. And then maybe hyper geometric functions, known functions, okay? So then you say this to a mathematician, and he will humiliate you, because your definition of analytically solvable depends on what you know which is kind of psychological fact. Okay? It has nothing to do with mathematics. Okay? So the fact that but physicists, you can catch a physicist anywhere and say, what is analytically solving an equation? I will tell you this, what I told you. And this is nonsense, actually. Okay? Because this is not a mathematical, if you want a mathematical definition, then you cannot say it depends on what I know. Okay? This would be, maybe you are ignorant, and for one person you say it's solvable analytically, and for the other not. So this is nonsense. What is important for us is, okay, so in practice, sometimes we will say analytically solving in the sense that this is just a shortcut to say I can write this in an easy way. It's a sine, or so it's a logarithm, or exponential, and so on. Okay? Most of the time, there will be, say, we want to study competition between two species, and there will be equations that will describe this, and I think probably already in this week we will have competition, and then you have the equation, and actually we will have two equations, and then we will discuss this later, okay? And then you cannot write the solution using sinus, cosinus, exponential, logarithm, fractions. No, you cannot do this. Okay? Then you say, okay, but the solution exists. There is a function, because not all functions have to be written in terms of this new known functions. A function can be given by a table, for instance. Table of numbers, that's a function associated to a certain entry. In our case, this entry will be of this time, the number of the size of the population at that time. Right? So you can give this a function as a table. Okay? This is one way to write a function. Okay? And this does not involve known functions. Then you say, okay, but tables, we don't like tables. Okay, yeah.
I'm sorry, I'm not really following, so can you give me a concept of function?
The function for our case is just it's a function in the sense that you give an entry, which is time, okay? And the function n of t is the size of the population at the time t, okay? So this is, and we have considering that t is a continuous, the time is flowing, okay? We can also say the time could be not continuous, it could be 1, 2, 3, 4, but we are not doing this. We are saying the time is flowing. So t is a real number, okay? Not a discrete number. And to every time, we assign the size of the population. This is the function. That's enter time gives you size of the population at the time. Okay? Yeah, say. Okay.
Well, you said that the Malthus law is a linear equation.
Yeah.
But why the solution is not linear?
Because linear equations don't have linear solutions.
And why I do not understand what is the solution in this case?
The solution is this function here, okay? So, this associates to time t equal to 0, the exponential of 0, which is 1, and gives you n0, okay? And n0 is your initial population. Say it's one individual, and it's n of 0 would be 1. Then, say after you want to know the population size after 1 hour, then you put t equal to 1, and you will have n0 exponential of this parameter only. Okay? So this is the function, and it's not linear. Okay? Most of the differential equations that are linear have exponential solutions. Okay? Sometimes imaginary, sometimes complex exponential, but that will not be our case most of the time. And linear equations have usually exponential, it's more or less. Okay? And so this is, and you can, if you have had some calculus classes, we can verify that this is actually a solution. How? I take this function and I put it here. Okay? So I want to calculate dn dt, but now n is this. So this is d dt of n0 exponential of r times t. Okay? And this derivative, n0 is a constant, so it gets out of the derivative, n0. Then you have d dt of exponential of r times t, and the derivative of an exponential is just r times n0 e to rt. So I calculate the derivative. Okay? So I'm just showing you that this is actually a solution of this equation. Okay? This function, I want to know if this function satisfies this equality here. Okay? So I have to calculate the derivative on my left-hand side here, the derivative, and I just calculated the derivative of the exponential. Okay? So this gives you that. And then I want to know if this is equal to this. So this is the derivative. Now, to be a solution, you need to know if this is actually equal to r times n. But it is, because you have the r here, and n0 e to rt is actually nt. Okay? Therefore, dn dt is equal to r times n. Therefore, it's a solution. Okay? That's the way it works. So we have a solution. Okay? And we are happy to have the solution. And you will have a whole course about what do I do if I don't know the solutions by functions analytical. Okay? That's the course of Renato Coutinho in the afternoon, which is computational methods. And will be, in many senses, be connected to solving equations on the computer. Okay? So we will discuss this later a little bit, because now I want to discuss the biology which is behind this. Okay? So before we start with the biology, let me just say, okay, nice. Now, it's many times, in order to understand things, we just do a plot of the function. Okay? Instead of writing or giving a table, you have a plot. So you put here one axis, which is n of t, and here the axis is time. Okay? And here's time equal to 0. At time equal to 0, the population is n0. And the exponential function is something like this. Okay? So it's exponential growth. Okay? You could also plot it instead of n. Sometimes we do. We plot the natural logarithm of n, okay, by time. You have some initial value here, and then the logarithm of an exponential is just what's the exponent. So it's just something like this. Okay? So exponential growth on a logarithmic scale is just a straight line, and otherwise it's this exponential function. Okay? Well, now, okay, this is still a little bit abstract, because then you can raise your hand and say, okay, I want to study a population of, I don't know, of elephants in Africa. What is R? Well, R is a parameter, yeah? How do I know R? Okay, that's the problem. It's the balance between death rate and birth rate. You would have to go and measure this in the field, okay? Yeah. So, however, there's a better way also to understand this more intuitively, which is calculating the time it takes for the population to double its size. I have n. How long it takes to have 2 times n, okay? And this will be related to R, and we will do this right now. So before this, just again, equation. I told you that this has units here, okay? Time is being measured in some units, seconds, years, hours, okay? And this is the population size, because it's population divided by time. So on this side, you also have to have population divided by time. Now, that's a basic principle of any model, that your units on one side have to be the same units at the other side. You cannot have 1 hour equal to 5 people. This is nonsense, okay? So you have here individuals per time, and then you have to have individuals per time here, and you already have individuals here. Therefore, R has to have the units of time to minus 1, 1 over time. Then you have, if the usual way to write this is to write this. The units of R is 1 over time. Okay? The units of R. It's not R, it's the units of R. Okay? Therefore, 1 over R has units of time. Okay? Okay? Well, now, so this is our first parameter, and it's a parameter that is what we could call a mechanistic parameter, in the sense that it can, in principle, you can, if you have a population that's in the lab or whatever, I mean, you can calculate birth and death rates observing the population, take the difference, and then you have the law of Malthus. You know R, you know N0, you know everything, and you could predict the population. Obviously, this is not true in the field, because we are putting here only birth and death in linear terms, and obviously it's not the model that will work in the field. Okay? We have to modify this. Okay? And this course is about how to modify this to make sense. Okay? But in the first point, this is it's a mechanistic parameter. Okay? And sometimes we don't have what is non-mechanistic parameters? We will learn this right now in this course, not now when we discuss competition. But sometimes we will have parameters that cannot be measured at the level of the individuals. Okay? Then this is said to be a non-mechanistic parameter. Okay. Okay. So now I want to calculate the time it takes for a population to double the size. The first thing you could object, say, maybe a population of 10 individuals takes 1 hour to double the size, but a population of 1,000 individuals will take a different time to double. Could be. And actually, in general, it is, except for exponential growth. And so with exponential growth, the doubling of the time it takes to double the population is constant, and I will calculate this now. Okay? So I have N0. Okay? But I want to know how long it takes to get 2 times N0. And I have that N of t is N0, e to r times t. And I'm supposing, obviously, that r is positive, that births dominate, okay? Otherwise, this is, I should have mentioned this, I forgot to mention. This is r positive, okay? Now, r negative is just exponential decay, okay? Okay, that's the exponential functions. Now, okay, so I'm taking positive because we want to calculate the doubling time. So now I want to take, I will call the doubling time T index D. T index D is the time, doubling time. And I will say at time T index D, the population has doubled. Therefore, it is equal to 2 times n0. Okay? That's what I want. Now, I can cancel this, and I have not a differential equation. I have just an equation with an exponential, and I then take the logarithm of both sides. So if I take the logarithm here, the logarithm of exponential times r times t is just r times t. And the logarithm of the other side is logarithm of 2. Therefore, the doubling time is just logarithm of 2 over r. And this is more intuitive to talk about doubling time than about r, which has this weird dimension of times to -1. It's measured in 1 over seconds or 1 over hours. This is more intuitive. Okay? I actually forgot to bring something in. That is, there's a book written by a guy called Gotelli, which is a basic book. You have usually the book of it's called A Primer of Ecology, and in Portuguese it's just Ecologia. And it's even translated, and it's usually given in population dynamics, population ecology courses in the masters. So I teach this, for instance, at University of São Paulo at ecology. And okay, I forgot it to bring it, Gotelli has a list of doubling times. Okay, how long does it take to double, for instance? So this can be very different things. For instance, if you go for microorganisms, for instance, E. coli, okay, which is a size of micrometers. Okay? So E. coli doubles the time in 20 minutes. Okay? But if you take an elephant, this will be years. Okay? And humans, obviously, also. Right? So this can have a very, very diverse range of values. Okay? So now I want you to make an exercise. We will do it together. It is the following. Exponential growth is something very, very strong. And it's very, very rapid, very quick. Okay? We saw this also, for instance, with COVID. I remember that I was interviewed by Rede Globo just to explain what's an exponential growth. Okay? Because that was at the beginning of 2020, and the report again, and then I was at Fantastico showing what is exponential growth. Okay? So it is, and then I mean, exponential growth is something that is, for instance, in epidemiology, it's always a problem because, you know, an exponential, if you really plot an exponential, it starts more or less softly, okay? So maybe you are not sure it's exponential, it's just another function, okay? But then it goes very, very quickly, okay? So now my question is, and I want first your impressions, I mean, just your gut feeling. How long does it take to cover? I have one E. coli, one E. coli, which has the size of 10 to minus 6 meters, the order of size. Okay? And in it doubles time in 20 minutes, So how long would it take to cover the Earth with a film of E. coli? What do you think? Let me see your intuition about this first. Everybody, you don't need a mic in this case because you can. Okay, what do you think? How long would it take to cover the Earth with E. coli? If the exponentials, obviously this is a fantasy because obviously E. coli, I'm not taking into account that you need nutrients, I don't take into account that there's the space and so on, but I just want to know how long would it take in this toy model to cover the Earth with E. coli if E. coli were to grow exponentially. So I want a few years. I didn't hear. A week. So out of week, 1 or 2 weeks. Huh? Little, but how little? Weeks. Okay, weeks. Hours to days. 2 days. 2 days. Yeah. They are just reproducing. Yeah, just reproducing. Okay. Yeah, that is. They are eternal, not like us. So, okay, you see, we have from years to hours. Okay. So now I want you to calculate. How can you calculate this? So I don't want every person now has to calculate. I mean, let's collectively calculate this. Okay, what do you need in order to calculate the time it takes to cover the Earth with E. coli? What are the things that you have to know? Size of E. coli. So we will consider the size of the E. coli. We will say it's actually more cylindrical thing. Okay, so it's more or less. So you need the size. I mean, you need the surface actually. Okay, because you want to cover the surface of the Earth. You need the surface. So it's not 1 micrometer. It's actually more or less. I have it written here. So 2. So okay, E. coli. Let me. Surface, I would E. coli. Okay? It's more or less 2 squared micrometers. So it's something that's more or less a cylinder, which is 2 micrometers times 1 micrometer of radius. So it's more or less 2 squared. So what you need else? Size of the Earth. Size of. I will not put. I will put T for Terra, and size of the Earth. You can Google it, okay? But now we are not actually aiming to be very precise. We want the order of magnitude, okay? So this is something that you have to get acquainted when you do quantitative ecology and anything that has, or epidemiology. You have to know more or less. You will always be interested in not necessarily on the precise values, but the order of magnitude, okay? And because, well, obviously the surface actually of the Earth is very difficult to calculate actually because there are mountains and this and that and so on. So we want an approximate value, okay? If you Google it, I think it gives you 510 million, okay, 510, make it 500, okay? Better, okay? So the size of is more or less this here. It's 500 millions of squared kilometers. But you have to transform kilometers. I mean, unit, this is in micrometers, okay? And this is in squared kilometers, okay? And you need to compare. What do you want to do? You want to divide one by the other in order to know how many ecoli I need, okay? This is actually, I wrote it down in meters, so it's 5, 10 to 14 squared meters. Okay. So now I have to either put everything into micrometers or take the micrometers to meters, which is the easiest thing. Okay. This is 1 micrometer, this is 10 to minus 6 meters, and this is 2 times 10 to minus 12 squared meters. Okay? What do I do now? Yeah, okay. So you have to do the. Okay. So, how many times? Okay. So what? In order to do this, if I say I have to divide, say for instance, if I want to know the number of people that can come into this class, okay, I need to know the surface of the class. Say that's 10 by 10, 100 square meters, for instance. Okay, every person has 1 square meter, more or less. Okay, so I have to divide the size of the classroom by the number of persons. And here I divide the size of the Earth by the number of ecoli. Okay? By the size of ecoli. So the number of ecoli that I need will be the size of the Earth divided by 2 times 10 to minus 12 square meters. Okay, so meters in meters go away. This is a number. This is the number of ecoli that I need in order to cover the Earth with ecoli. Now I start with 1 ecoli. And the doubling time is 2. It's 20 minutes. Okay? So this here is 20 minutes. Okay? So we don't want to use minutes because this will give an enormous number of minutes. Okay? So let's do hours. Okay? So 20 minutes is 1/3 of hour. Okay? And the units is hours. Okay? Okay? Then I can calculate R. Okay? So 1/3 is equal to logarithm of 2 divided by R. And once I know R, I can use the solution of the exponential growth in order to know how long it will take to double the Earth, to cover the Earth with ecoli. So this is that, therefore this is equal to, it means that R is just logarithm of 2 divided by 3. Okay? In hours. Okay, doubling, this is 1 over hours unit. Okay? Now, I want to know how long it takes to cover the Earth, starting with 1. Therefore, I will use my exponential growth equation. I don't need the equation. I already solved the equation. Okay?
Is it divided by 2 or multiplied by 3?
What?
I think the 3 is multiplying the
Ah, okay. Elementary mathematics. Okay. Yeah, sure. Sorry. So now, can anyone calculate what's the value of a logarithm of 2? Anybody can calculate quickly? It's 1 point. 0. 0.69 times 3. I want to put numbers here, okay? 2.08, make it 2, okay? So that's the value of R. It's more or less 2, okay? So now, I want to know the time if I start with 1, therefore n0 is equal to 1, and n of t should be this thing. Okay. This is 5 divided by 2, 10 to 26. Okay? So I want n to be this value, 5 divided by 2, which is 2 point, okay, let it be like that, 2.10 to 26 is equal to 1 exponential of 2, which R is 2, the time it will take. Okay? I want to know the time. I know the population. I want the, not n of t, I want the inverse, okay? So now I have what to do. I take the logarithm of both sides. The logarithm here is logarithm of 5 over 2 plus the logarithm of 10 to 26. And this is equal to 2 times t. And this is logarithm of 5 over 2 plus 26 logarithm of 10 equal to 2 times t. Okay? Good. Now, can anybody calculate these values for me? Logarithm of 2.5 is more or less the same as the logarithm of 2, which is small.
Around 60.
Yeah.
The left-hand side is 60.
Now, this here is
The whole thing.
yeah, okay, just a minute. This we can neglect. Why? This is 26 times something that's still bigger than 1. And this is a small number. And we are calculating things approximately. Okay, so just disconsider. Okay? Better. So you have, what's the value of logarithm of 10? The natural logarithm of 10?
2.3.
Times 26 will you give you more or less the 30? 60. 60 is equal to 2 times t. T is equal to 30 hours. 30 hours. 1 day and 6 hours. Starting with 1. So this is to illustrate how enormous is exponential growth. Okay? So in 30 hours, you have the number of better put in this way. In 30 hours, I would have the number of ECOLOGY that could cover the Earth. Okay? So this is something. Then you say, okay, but even if I didn't take E. coli, and I take elephants, which have, I don't know, doubling time of maybe 100 years. But we have a lot of time, so we should have been covered by elephants, by E. coli, by everything. So no, obviously this is not okay. But then, what does it mean? We have to have better laws, better models. And what's the problem with our model? That's the birth rate and death rate are constant. That's what I have postulated. But I mean, if you have a lot of individuals, maybe there's no nutrients, and then the birth rate will be smaller when you have a lot of individuals, and the death rate may be bigger, and so on. So maybe the death rate and the birth rate depend on the size of the population and are not constant. Okay? So this is what we will do next class. But now, just let us consider a little bit more the Malthus law. Because, you say, and this will be very typically of how to build models in ecology. So you would say, okay, Malthus law is not true. Okay? Should put it put it away. That's not a good way to pursue. Physicists would like to do this usually, okay? But actually, Malthus is a model, not so much a law, but okay? And we don't want to, we want to proceed by building upon simple models and incorporating more and more biological facts that makes the model more realistic. That's what we want, okay? So we don't throw away. Actually, the model of Malthus should be phrased like a population, according to Malthus law, population increases exponentially if nothing, if there are no barriers to death, to the increase, if there are no, nothing is holding it, okay? So, and then you come to the conclusion, okay, there will always be happening something that will not allow for the exponential growth. For instance, your E. coli is on a petri dish size, okay? So exponential growth, actually, when you do experiments with E. coli, it is perfect exponential growth. It's the textbook example is E. coli. It really is exponential, but then there's a moment that the experiment has to stop. And then, okay, you won't cover the earth with E. coli. Okay? So there will always be something, right, that will be something that will be which holds the mentioned, and it will depend on many things, right? And it can be that whatever. Okay, we will discuss many things that we will show next class. We will already show something which is not exponential. Okay? But we can also learn from this example of E. coli in the lab that I told you it's actually an exponential until you fill your experiment, that maybe exponential growth is not, a population will not grow exponentially forever, but maybe they have a phase of exponential growth and then it goes slowed down. Or maybe it will decrease, or whatever will happen with it. Okay? But maybe it's just a range of time where there are so many nutrients and so many things that there's nothing that holds the population. Then there's space, there are nutrients, everything. Then you have exponential growth, but then nutrients get depleted, space is finite, and then you will have slowdown of the growth, and that's it. Okay? So it is useful to think about exponential growth as a phase of exponential growth. Okay? And that was, with COVID was actually the thing at the very beginning. The point is, we had an exponential growth initially, and then something happened. Everybody closed the home, and whoop, something happened, because in this case it's behavioral, okay, of humans, stay at home. And now, to finish this discussion, let me just mention that there is something which is not the same, but is similar, which is the law of inertia in physics. The law of inertia in physics says that the motion of the state of motion of a particle does not change. it's a constant velocity, constant speed, if nothing opposes this. And this is like Malthus, okay? Malthus says exponential if nothing opposes. And Newton says constant speed if nothing opposes. Therefore, both of these laws are not in a more, it's more an epistemological discussion. They cannot be verified, okay? Because law of inertia, obviously, the implications of the law of inertia are so many, and everything that you can actually verify, blah, 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 imply that the law of inertia should be proved. But now I want to know. I don't want this. I want to make a measurement, an experiment, and you can't. Because, I mean, you can start with a nice table, go to the new materials department and make it frictionless, everything, high-tech, and so on, but it will have some finite size always, okay? And, well, then you cannot verify. But we kind of incorporate into our theories this, okay? So, and then there's another thing. This is more discussion like in physics, but this is useful when you think in more general terms of quantitative ecology also. In physics, you have, for instance, the law, Newton's law of gravitation, yeah, which allow you to calculate the orbits of the planets around the sun, and so on. Very nice, very precise, and people say, okay, that. Then, sometime back in, I think, beginning of 19th century, if I'm not, you see, to measure the orbits of, with the development of good optical telescopes, you can measure things more precisely, and then you see Jupiter, Saturn, and then Uranus, and then Neptune. Okay, not Neptune. Then what people saw was that Uranus has an orbit which is not in agreement with Newton's law. So, what do you do? Is Newton's law wrong? That would be. But you know, it was so useful. I don't want to throw away Newton's law because of Uranus. But then, actually, it is not Newton's law that was wrong. It's your model of the solar system that was wrong. And if you suppose there's something else, which is Neptunus, and then you can calculate where the orbit of this putative, this new planet, in such a way that it would make the influence on Uranus be exactly what you observe from Uranus. And doing so, then you can point your telescopes and try to find Neptunus, and that's what happened. So the theory was correct, but the model was wrong. Now come end of beginning of 20th century. There's a problem with the orbit of Mercurius. Mercurius does not behave according to Newton's law. What's the first thing you would say? Model. There's a new planet. And it actually had been tried. People tried this. And the new planet was Vulcanus. And never found this one. Nobody found Vulcanus. No Vulcanus. Then maybe the proximity of the sun, there are many irregularities. So people tried everything. And the point is, the theory was Newton's law are not the definitive theory about gravitation. It's the general relativity of Einstein that explains the orbit of Mercurius. So you see, they have an interplay between theories, laws, and the model of the system that they are studying. The theory, let's say Newton's law is a fundamental theory that should be applied to anything. And then you have a concrete example, solar system, then you have the model of the solar system. And then we will have, in ecology, we will always have this kind of thing. We will always have to have a model of what is important, because there are so many species. And then you want to study the, I don't know, a certain species, but a certain species has interaction with many other species. How can I proceed? Then I will have to make a model of my, say, ecological community. That say, if I want to study, I don't know, go back to, I don't know, zebras, then I will take into account lions, for instance. Okay, so you will make a model of what's important about your system. And that's, it's not the same as in physics, and but there's this also in physics, because when I tell this to physicists, they say, oh, this is so different from physics. No, it's actually not so different from physics in the sense that that you have models and theories. What is very different in ecology and in other areas of biology from physics is that you cannot most of the time you cannot manipulate your individuals in a lab and make precise measurements. That you can't. So there is a problem. Say I have a tree, and I want to know the number of, I don't know, ants on the tree. And I'm not allowed to cut the tree, but I will have to use a statistical method to infer from some observations, partial observations, I will infer the population. Therefore, there comes into play statistics in a way that physicists never use. I mean, ecologists know much more statistics than any physicist. Not any physicist, but most physicists, because most physicists just do, I don't know, the mean, standard deviation, that's the statistic. So precise in the lab, the things are so precise. You can have 10 to minus 10 precision of certain measurements and whatever, and many things that are very, very precise. And that's because it's you can manipulate, okay? In ecology, you can't. So I want to know the population. I'm interested, say, population dynamics of how do you say this in English? Onças, for instance, in the state of São Paulo or in a certain forest. Okay? You don't know the number. I have to put cameras, or you can go. There are other methods, but say cameras. But cameras is also partial observation. I mean, you will say sometimes one of the individuals, then you have to decide if the next day is the same individual or not. And then you have somehow to build a statistical model to infer from your, say you have 1 year of observations with photos, infer how many individuals you have. And this is the way that ecology is built. And this means that uncertainties are very, very present. Okay? So there's there's no sense in saying very precise numbers in ecology usually, unless you have microbial biology. Okay, then it's fine. But otherwise, no. Otherwise, you will always have approximate. I have 10 individuals plus minus something. Okay, and all of this has to be calculated, and that's your next course with Paulo Inácio Prado is about this. Is about this practical things that you cannot do if you want to do ecology in your life, population dynamics, or anything in ecology. You have to know the statistics, statistical modeling, in order to calculate the sizes. Here we are doing the deterministic and the laws and so on. But then there's a problem of how to relate this to an experiment. or to better saying, to an observation, because ecology is largely observational. It's like astronomy and cosmology. It's also, you cannot manipulate the stars. So astronomy and people that do astrophysics and so on, they know more statistics than the average physicist because they also have only observations. They don't have the real experiments in the lab. Right? So this is a very big difference. And you should never think that ecology, quantitative ecology, will give you results like the results we have in physics, where we have labs that can manipulate everything. Right? Okay, that's it. It's time for a coffee break. I promised to tell you about the books. I will leave them here for some time. These two books are more mathematical. You know, you have to know more or less well. Okay, this here is Jim Murray, Mathematical Biology, an introduction. And this is Mark Cott, which is more mathematical than this one, but it's mathematical ecology. So, but if you don't want to see these mathematical books, there's this book by Mathiopoulos, How to be a Quantitative Ecologist. This is written for ecologists, okay? And then you have all the math. I mean, what's a derivative? What's an exponential function, and so on. Okay, and in this here, this most ecologists know. This is a textbook, and this is just to show people from math and physics how is a book of ecology with us, not mathematical ecology. Okay, this is Bagon, and there's a lot of things here. Okay, just for you to have an idea. Okay, so see you tomorrow, and tomorrow we will go and study what is called logistic growth. Thank you.